guess what I'm gonna do is I'm gonna kind of scribble along and we'll talk, rather than me actually doing all of that. So you have this trapezoid. Let's see. It looks something like this here. And if you construct a symmetry line for ROUN, it's gonna be, essentially you're gonna have this, correct? You're gonna bisect each of the bases, because they say that it's an isosceles trapezoid. So that means one side is a mirror reflection of the other, of that symmetry line. Then we need to find the center of the circle that contains all the four vertices. So do you guys remember how to find the center of like a triangle?
Yes.
Yes. How?
Colin Bacon.
What I did was from each three of the vertices is I took my compass and then drew and then opened it like to the length, like the diameter of one of the side lengths, and then did circles on each, like on each vertice, and where each circle met was the extent of the length.
Okay. So with a triangle, how do you find the center of the triangle?
Perpendicular bisectors to the sides.
Yeah, perpendicular bisectors of all three sides will cross at the center of the circle. Same thing will happen here. So this is a perpendicular bisector of the two bases already. So all you had to do is a perpendicular bisector of this side, and it would show up somewhere around here. And then if you did a perpendicular bisector of this side, that ends up being the center. And then you open up your drawing compass from that center to any one of the 4 points, draw a circle, and you should have that trapezoid's vertices all sitting on the circle, or be really close. So if you did a tracing and you were off a little, you know, it could have been your perpendicular bisectors, you know, you're off by the width of a pencil lead a couple of times and everything slides around, but that's where it would end up. Somewhere like the midpoint of the longest base. Okay, then eight. Okay, so we have triangle ISO. It's isosceles with IS equal to OS. DZ is parallel to IO. So IS is equal to OS. So, yeah. I'm not going to mark because then that might mean that SD would be, but this entire length is equal to this. Okay. So they conclude that triangle ISO is isosceles with IS equal to OS and DZ is parallel to IO. What is that? Yeah, given. Everything starts with given. The book will never mess with you and give you something other than given. Measure of angle I is equal to the measure of angle O. So why is I equal to O?
Triangle with base angle theorem?
Yeah, it's isosceles triangle base angle theorem. So we have the sides that are equal in length, therefore the base angles are equal in measure. And then zoid is a trapezoid. So that's this right here on the bottom. Get rid of the top of it. Why is it a trapezoid, given what you see? So what do you see in the trapezoid? What's marked? Sally?
Because there's two just set of parallel lines.
Parallel lines.
And there's an angle there too.
Those base angles are the same. So what does that do?
Isn't
Yes.
it just the definition of a trapezoid?
I think so. I think that's just the definition of a trapezoid, isn't it? That's what I was thinking. So by the definition of a trapezoid, then zoid is an isosceles trapezoid. What makes it isosceles? Definition, what's the definition of an isosceles trapezoid? How is that different than a trapezoid?
Because it has two angles that are the same and parallel lines.
Triangles that are the same and the parallel lines?
Well, yeah, if you look on the
Yeah,
quadrilateral
that-
hierarchical.
Yeah, that's right. We didn't need to know that these were even the same to know that it's a trapezoid.
Yeah, but if they're the same. That's
Right. So for letter C, that was just the definition of a trapezoid, which didn't include these angles, the base angles being equal, but once the base angles are equal, then it's an isosceles trapezoid. Okay. Then we'll go with that. And then 17. I'm gonna draw 17, right? Yikes. Where's your bets? Just come to here. Is there an OC? No, there is. OC. Then we gotta get a circle in there. The center P. Is this D on the drawing?
Yeah.
And then that circle's gotta hit over here, right? And the circle has a center that lies in the middle here. Ooh. There we go. That's it. Is that, oh, what's that? It's gotta do this.
It's on the plan. Oh.
Oh, it's gonna hit O, doesn't it? Yeah, okay, I'm sorry. Couldn't hear you through the, there we go. There, that makes it easier. Does that work? And then, and then there's E. E, which is right here. Okay, so we need to find the measure of ABC. ABC. So we need to find this. And is it this one? Okay, AFC. And is anything known? Arc DE is 140. So from D to E is 140. So this is 140. Is anything else known? O and P are centers of the circle. DE is 140. Okay. So starting with that right there. If this is 140, how can we work backwards from that? Galen?
O is 70.
This one is 70 right here? Is that right? So angle DOE. How do you know it's 70?
140 divided by 2.
Okay. And since this blue line from O to E and O to D is an inscribed angle, that angle is half of that arc. Okay, now where can you go?
You can find the measure of B based off of O.
You can find the measure of where?
Based off of O, because that will be 35. Like the arc of O
The arc of O.
is, like B is the arc of O divided by 2. Right?
I'm not sure what you mean by the arc of O, because O is the center.
Like, O, if O equals 70, B has to equal 35.
So O is 70.
Yeah.
This has to be 35. Oh, because from this 70 goes,
Okay, yeah, no, that's what I meant. Like the arc of
okay, so this is a central angle
Yeah.
of 70, which makes this 70, makes arc AC 70. And because B is an inscribed angle that ends at A and C, this has to be 35.
Yes.
Okay. Yes. Then what? How do you get up here? Check it.
It's the same as B because they both open up to 140, which is AC.
So from A to C was 70.
I thought it was 140.
D to E is 140. Because this right here, from this little section that I'm outlining, that is an inscribed angle of circle T. And we were told that from B to E is 140, therefore the inscribed angle is half of that, 140, which is 70. But then if we look at circle O and we ignore the black circle here in the middle, O has an angle, it's a central angle of 70, therefore it's going to open up to an arc of, you're right, that's 140. Is that, wait, no, I'm sorry, no, it's not, it's 70.
Yeah.
It's because O is a central angle, that degree will be the same as this arc. Okay, so this is 70 out here. Then ABC is an inscribed angle, which is going to have half the measure of this arc. So now how do you get AFC?
Wouldn't that be 35 also?
Because
It's going to the same point.
it goes to these 2 points out here as an inscribed angle. Yeah, that's 35 degrees. Okay. Yep. Time to go? Forward?
Yes.
Is that enough?
Yeah.
Okay, we're going to skip 6, 7. And we're going to go to 6, 8. A big part of 6, 7 is stuff that we've done in middle school. And if you say, oh, I wasn't here for middle school, it's still not a big deal because you probably did it wherever you were. 6, 7 spends time talking about rotation symmetry. So things like C stars. The C stars that have 5, I don't know what they call those. What are they? Arms? Yeah, 5 arms. So a C star that has 5 arms, for example. This is my C star today. How many symmetry lines could you draw?
2, 3, 5.
Probably 5, huh? One right down here. 2, 3, 4, 5. So there's 5 lines of reflective symmetry. And if we think about all of this, get rid of the lines of symmetry. Now we have a red C star. If you were just going to take this and rotate it, how many times would it stop upon itself before arm number 1 got all the way around?
5.
It was once, twice, 3 times, 4 times, 5 back to home. So, how many degrees of rotation total? 360. So, that n is how many folds of symmetry there are. So you could take your C star and you could fold it 5 ways, 5 lines of symmetry. So, in this case here, it's 360 divided by 5, which is how many degrees? So it has 5-fold symmetry of 72 degrees. So you could say it stops at 72, 144, and keep adding 72 until you get back to 360. That's kind of how it was talked about in middle school. So that's all we're missing from 6-7, I think, that we need to carry forward with. So then we'll go to 6-8. And that's going to be regular polygons. So regular polygon is convex, and the angles are all congruent. So in other words, they're all the same. So if you had, for example, a triangle that was regular, a regular triangle, all 3 angles have to be the same measure. How many degrees would each of them be? I'll back up. If you have a regular triangle, all 3 of the angles are the same measure. How much would each angle be? How much?
60.
60. 180 divided by 60. If you had a regular quadrilateral, what shape would that be?
Square.
Square. So how many degrees for each? 90. If you had a pentagon, we got lucky with that one. If it's a regular pentagon, all 5 angles need to be the same measure. What's that going to be?
72.
How much is it?
72.
Is it 72? Yeah, just like the starfish, right? So what was the equation that we used for this?
360 over
Not 360. Well,
It's
ooh,
n times 360 subtract 180.
n times
360, or 180.
And minus
2 times 180. That's the total, right? This is how you find the total number of degrees. So with a triangle, 3 minus 2, which is 1 times 180. A square is 4 minus 2. 2 times 180 is 360. And then this is 5 minus 2, which is 3. 3 times 180 is 540. So that's the total number of degrees. But I want to just find 1. So what would you do with this to find one of those?
Divided by however many angles there
Okay, and how many angles, or how many sides are there?
are.
And, yeah. That's what's going to give you the number of degrees of each of the angles of a regular polygon. So, try my luck. So there's a regular 6-gon. Yeah, Mar.
What is that equation?
This will be equal to the number of degrees of each interior angle of a regular n-gon. Regular meaning that they all have the same measure. All angles will be the same measure. So an equilateral triangle, a square, a regular pentagon, a regular hexagon, and on and on. So how about a hexagon? A sixth-gon. What's going to be the number of degrees of each interior angle? Okay, go.
120.
Is it 120? Eighteen divided by 6 is 3, so this is 30. 6 subtract 2 is 4 times 3, which is 12, times the 0, which represents 10. 120 degrees. Okay, so that means the bisector of that angle is how many degrees on, or is going to create two angles of how many degrees? 60. So there's a 60, there's a 60. So what's going to be the bisector? What are the two angles that are on either side of the bisector for?
6.
That's going to be 60. So this is 60, this is 60, this is 60. So what does the angle have to be on the inside? That's got to be 60. So everything's 60. It's like having 6 equilateral triangles that got shoved together. Remember those little pattern blocks in kindergarten? They're up in the middle room. Yeah. So everything's 60. So let's construct this. You have a drawing compass? Make a circle in your notebook. Yeah, all you need is a circle for now. See how this is, well, that's gonna be way too big. Something's gotta go. So, mark your center, draw a nice pretty little circle, and then do this. Mark any point on your circle. And then if you just draw in a radius. So far we've done no measuring, right? Okay. Now, if we're going to have an equilateral triangle to construct this hexagon, we need to have a triangle that's drawn here that has 3 sides that are the same length. So what you can do is you can keep the radius the same, and then just go up to this point on the circle and measure down the circle and make a little mark. And that is also going to be the location to draw another radius. And so I just went up here, and I took my drawing compass, made a little mark. When I go to that point, make another mark, keep working around, and we should get back to where we started. yours is gonna look better than mine, cause this is a big old floppy sloppy thing. And then you got a 6-gun. Or your floats. Yours done? What do you have left to do though? Not a circle, you want it to be a hexagon. Yeah, I'd leave your circles there if you want them, your arcs. Well, let's do that. Let's do something to it. Let's have everyone has theirs done. Let's change it. Let's make it a different color. So it's hexagon. It's inscribed because each of the vertices lands on the circle. So just like when we did the inscribed angle, compared to the central angle, the inscribed angle was like out here. The angle vertex was on the circle. So from here to the central angle, which would be 60. So that's an arc which is going to be twice that, so that's 120. Okay, now, can you construct the perpendicular bisector of each of the sides of your 6-gon? How do you do perpendicular bisectors? You did them for what was that question number? One of them that was up here, like number 8 or something. Yeah, Jacob.
So you're gonna take your drawing compass and create like diameter greater than half the length of like a side, and then go to like select 2 points that are next to each other, and then like create a point like a dash above and a dash below, and when they both intersect, you can take your straight edge and then draw a line. That makes sense.
Yeah,
For this instance, could you just do it on one side because you have the same height?
you probably could. Yeah, if you use the same radius, your arcs could be right here in the center, or doing this side, for example. So then all you'd have to do is put an arc outside,
Yeah.
and then connect that intersection to that center.
Well, if you have a long enough thing, could you just go back here?
Yeah, I think so. Then you all of a sudden would have, you could have symmetry. You think of it that way. So once you go through here and you draw this, by symmetry you could also draw this. That's what you're saying. So then what we can do is we can take each of these vertices and turn it into a 12-gon. Luke said he wants to turn it into a 24-gon. Just kidding. Every one of the sides ends up being the bisector of an isosceles triangle. And so as you guys are finishing up that, a triangle has 3 sides. How many folds of symmetry does it have? In other words, how many lines of symmetry could you draw? 3. Bisect each side and go through the vertex opposite of that side. 1, 2, 3. How many lines of symmetry in a square? 1, 2, 4. How many in a pentagon?
6.
Penta.
Oh, 5.
Hexagon.
6.
So the number of sides of a regular polygon is equal to the number of folds of symmetry. And every one of the folds of symmetry ends up going through the center. So every one of these regular polygons can be inscribed in a circle. The center of the polygon is also the center of the circle. That's kind of all I have, other than numbers 1 to 14 and 18 to 21. Oh, and
Are we also doing 23?
yeah, I put 23 in there. Page 361.
361?
Yep, page 361. Question number 23. Look at that right away. So if you have any questions, you can ask. And then 1 through 13, or 1 through 14, and 18 to 21.
Plus 23 or not?
Yeah, 23 at the beginning. Okay, 361?